Hello, everyone. Yeah, my name is Yongjung Kim, a KIA fellow at Peking University, China, started last November. First of all, I greatly thank the SOC and other members for giving me this kind of great chance in the current pandemic situation. And today, I'll I'm sorry, I'll give a talk about the Quasar Luminosity Function at redshift 5 with the Infrared Medium Deep Survey, shortly IMS. This work is related to my PhD thesis and was submitted to APJ and under the revision now. Now it has been widely known that the intergalactic medium or IGM has been almost completely ionized after redshift 6. As shown in this figure, the neutral fraction dramatically dropped at around redshift 6. But it was debated that what ionizing sources can maintain the ionization state of the IGM in the post-reionization epoch. Quasars radiate a huge amount of UV photons by accreting the materials into their central supermassive black holes. So they are regarded as potential contributors. The right figure shows the redshift evolution of UV emissivity from quasars, and as you can see, there are large scatter at high redshifts, which makes it difficult to determine the quasar's role in to ionize the full IGM or not. The reason for the large scatter in emissivity is mainly because of the lack of faint quasars, especially at -23 or -24 magnitudes, absolute magnitude. Yeah, and this figure shows the differential emissivity distribution as a function of the magnitude derived from the recent Quasar Luminosity functions at redshift 5. And as you can see, the emissivity efficiency peaks at around -23, 24 something. But unfortunately, due to the survey limitation, the number density of quasars in this magnitude range was uncertain. Yeah. The right figure shows the Quasar Luminosity Function, shortly QLF here at the QLF at redshift 5, and except for the Gialongo et al. In 2019, shown as some purple line, it seems that their parametric QLFs, shown as the solid lines, are in line with each other. But as I marked, each study has its own limitations, such as some survey depths, biased sample, or some limitation to some parameterization and so on. So here we try to derive better QLFs at redshift 5 by finding more faint quasars. Recently, our group have performed the Infrared Medium Deep Survey, shortly IMS, which is the NIL imaging survey. The imaging data in Y and J bands were obtained with the wide field camera on UCURT, and IMS covers over 100 square degree area on the sky and reaches the J band magnitudes of 23 in AV system. This kind of the imaging depth is appropriate to fill the deficiency of the faint quasars. So including the optical imaging data from CFST legacy survey, we have performed the high-redshift Quasar survey with IMS. The combination of these optical and NIL imaging data enables us to find faint quasars down to -23 magnitude at redshift larger than 5. In this presentation, I'll give a talk about the quasars at around the redshift 5. The red color from the sharp line alpha break is a key to find the high-redshift quasars, so the broadband color selection method have been well established. And we initially selected the 69 quasar candidates with broadband colors. Unfortunately, the dwarf stars also have similar red colors and can be interloopers. So we introduced the medium band filters, which have only 500 Armstrong bandwidth, and which allows us to obtain finer SEDs, like some kind of the low resolution spectroscopy. And this figure shows that it's efficient well. As you can see in the top panel, the high-redshift quasars colors are similar to the dwarf stars in broadband, but if we use the medium band colors, it is expected that we can easily distinguish the break of the high-redshift quasars from the dwarf stars red colors. On this medium band color diagram, we successfully narrowed down the number of the plausible candidates for the some redshift 5 quasars. For the plausible candidates, including the broadband salty or the medium band salty candidates, their spectra were obtained with the large telescopes, such as the Gemini 8-meter telescopes or some Magellan 6.5-meter telescope. And we already published 13 quasars in 2019, and here also identified some 8 new quasars. And consequently, we identified 21 faint quasars at redshift 5, while 18 of them are newly discovered ones. We include additional 22 quasars identified by previous works, which were also selected by our selection criteria. And in total, we have 43 spectroscopically identified quasars. Now we consider 2 cases for the case 1 for the broadband selection only, and case 2 for the combination of the broadband and medium band selections. The number of quasars in each case are 43 and 32 respectively. And we calculate the quasar selection function in each case, as you can see in the right figure. Note that we use the improved version of the high-redshift quasar model in our previous work. Also, we consider the photometric and spectroscopic completeness of our survey, as shown in the right bottom figures. The combination of these two gives the total selection probability. Using the total selection probability P, we calculate the luminosity function at redshift 5. First, we calculated the bin QLF using the well-known vulnerable Vmax method. The red and blue circles in the right figure are the bin QLF in case 1 and 2 respectively. And second, we calculate the double power shape quasar luminosity function QLF using maximum likelihood method, which are shown as the solid line with some shaded region of the 1 sigma confidence level. And note that in this calculation, we include the bright SDSS quasars in Yang et al. In 2016, shown as the orange circles in this figure. And in this work, we, for the first time, derived the parametric QLF down to -23 magnitude without any fixed parameters, and with some very flat fainting slope of -1.3. The QLFs in the both cases, case 1 and case 2, are consistent with each other. And considering the high success rate of our medium band selection, as we published before, especially at the faint magnitudes, wide area surveying medium bands will allow us to estimate the reliable QLFs at high redshifts, even without deep spectroscopic observations. When we compare our QLF with others, it shows some flatter faint slope of -1.3, as I mentioned, while the other studies suggested -2 something, as you can see in this figure. But note that the dust values in Yang et al. And McGreal et al. Have their own limitations, as I mentioned. And interestingly, our value of -1.3 is similar to recent HSC quasar surveys at redshift 4 and 6. Our QLFs are consistent with most. It's very interesting and currently is in working. Sorry. And our QLFs are consistent with most of the QLFs in previous works, as you can see in this figure, except for some Jialong et al. In 2019, shown as the purple line. At around -24 magnitude, they used the bin QLF from the small area surveys and covering only a few square degrees. So we can say that compared to the wide field area survey, we can say that their estimation in this magnitude range can be overestimated due to some kind of the serendipitous detections. At magnitude fainter than -23, Jialong et al.'s QLFs relies on the very faint X-ray quasars. But so We can think that the one possible explanation for this discrepancy between ours and Yongjung is due to the high fraction of the UV obscured quasars at redshift 5. But we know that the recent X-ray QLFs corrected by Shen et al. In 2020 show a good agreement with our results. We also calculate the UV emissivity by quasars under the several assumptions. Despite the extrapolation of our QLF at magnitude fainter than the -23, the emissivity efficiency at that magnitude is insignificant with our QLF. So we estimate the emissivity down to -8 in magnitude, and the observed emissivity is shown as the red circles on the right figure. And this value is the lowest value at redshift 5. However, when we consider the results from the large area surveys shown as some kind of field circles, all the points are in line with the model of the Hothem model in 2012 and other empirical models shown here as well. We also calculated the ionizing photon density by quasars, assuming the escape fraction of unity and Doppler shape of the UV quasar spectra. And we compare this with the critical density required to fully ionize IgM, shown as the gray thick lines and squares. And we suggest that only about 10 or 20% of the UV photons are from quasars. And it is up to 50% even in the extreme case. Therefore, we discredit that the quasars alone could provide UV photons enough to keep the ionization state of the IgM in the post-reionization epoch. So here's the summary of my talk, and feel free to ask your questions in Slack. And after this work to be posted on archive soon, and thank you for your listening.
Thank you very much, Yongjung. So we have a couple of questions. First of all, how did you calculate the 1 sigma envelope on the maximum likelihood luminosity function?
Yeah, wait a second. Yeah, maybe meaning this kind of the confidence level, and as you know, it is well known that using the maximum likelihood and the factor S, you can calculate it can be approximated to some kind of the chi-square distribution. So on the this parametric distribution of the S, we calculate 1 sigma confidence level for this parametric QRF.
Okay. And another question is, could the flatter slope be due to the completeness corrections applied by yourself and others compared to what others have shown?
I'm sorry, could you?
Could there be a difference in the slope between your luminosity function and other works because of the completeness, because of different assumptions on the completeness correction?
Yeah, it might be, but actually the method to calculate the completeness and the other thing is just, I think that it's very consistent with each other. So yeah. Okay. So I think it's not a critical thing, but yeah, but for some kind of small survey area, the completeness and some selection function might be important, and we think that the values that being the QLF from the small surveys might be overestimated. Yeah, so okay, but it's important to regarding the completeness issue.
And then another question: is there any prospect to follow up your sources in X-ray?
Any prospect for X-ray sources?
Yeah, are you going to follow up your observations with X-ray observations, or is there any possibility that you could do so?
Yeah, but you know, the X-ray observation is not easily accessible, and also yeah, but yeah, of course, then maybe there's some kind of the follow the wide field of X-ray observation required for the see this this kind of the discrepancy and solve the problem between them. But yeah, actually, I have no idea right now. It's good to think of it.